In this question, they want us to both predict the sign of delta S qualitatively and then actually calculate delta S for each of the reactions. To do that, you have to look up in Appendix 4 the numerical values for the standard entropy for all of the substances in these equations. Let's start with the qualitative determination first. First of all, entropy values are always positive. And that's what enables us to make a qualitative determination of the sign of delta S. So if you look at equation A, we've got hydrogen and oxygen on the reactant side of the equation existing as broken apart molecules, and then they come together to form a single larger product. There's less disorder in the put together product than in the separated elements. So if I were to predict a sign for delta S, it's a small or low positive number minus a higher positive number. That gives us a negative result for our sign of delta S. In the next equation, part B, we've got, first of all, recognize it as combustion. Combustion is giving off huge amounts of energy typically. For this one, since everything is a gas, we can consider the total number of moles of gas. We've got 6 moles of gas on the product side and 5 moles of gas on the reactant side. So if we're considering, all right, where do we get more moles of gas? It would be on the side with, or the more entropy, higher entropy values would be found on the side with more moles of gas. And so in predicting a sign for delta S, we've got a high entropy value, high positive number, minus a lower one. That should give us a positive result. And in the last equation, it's decomposition. We have a single put together product with relatively lower entropy than the elements that make up the product on the right side of the equation. So we've got a high positive number minus a smaller positive number. That should give us a positive value for delta S. Now we can verify all of that using the equation delta S standard equals the sum of the standard entropy values for the products minus the sum of the standard entropy values for the reactants. Unlike delta H, and as we'll come to learn delta G soon, elements and diatomic molecules do have standard non-zero standard entropy values. So if you look up in Appendix 4 the values for standard entropy for both elements and diatomic molecules, you'll see that there is a number, but if you read across that row, it's a 0 for delta H and a 0 for delta G. Okay, we can then apply this equation after looking up all of the standard entropy values for the species in these equations. In equation A, it's products minus reactants, so a lot like the delta H equation. We've got liquid water, and there's one of them. We're subtracting from that hydrogen, and the coefficient in front of oxygen is a half, so just multiply the standard entropy for oxygen by half. When you crunch the numbers, this one works out to be negative 163.5. The units are joules per degree Kelvin, not kilojoules, but joules per degree Kelvin, showing the per degree Kelvin shows us that entropy is indeed temperature dependent. Question B. Four times gaseous water's entropy, 189, plus 2 times carbon dioxide's of 214, minus the quantity 2 times methanols, which is 240, plus 3 times oxygens of 205. When you crunch the numbers, this one works out to be a positive 89 joules per degree Kelvin. And then lastly, part C. We've got hydrogen ion actually has a standard entropy of 0, which is unusual. It's one of the only species that has a 0 entropy. And 1 times 57 for the chloride ion, and from that we're going to subtract the quantity 1 times 187, and that gives us a negative 130 joules per degrees Kelvin. Okay, so if we fill in those numbers, we had negative 163.5, we have a positive 89, and a negative 130. Did our prediction match the actual numerical result? In part A, we predicted a negative sign for delta S, and we got it. In part B, we predicted a positive sign for delta S, and we got it. And in part C, actually in part C, this is a weird one. I didn't notice this until just now. Note the different states of matter. Yes, we're breaking apart hydrochloric acid, but in the put-together compound, it's a gaseous HCl. And on the product side, it's aqueous species that make it up. For that reason, this one's a tough one. It is a put-together compound, and by that virtue alone, you might say, oh, there's less entropy for the put-together compound. But counteracting that and actually outweighing that is the fact that we went from the gaseous state to something that's aqueous. So I apologize, this one is negative because there's relatively lower entropy in the aqueous species than we find in the gaseous species. So this should be negative as the sign of delta S, and that is actually what works out to be the result.